All right, AP, let's pick it up again. Talking about chemical kinetics, chapter 12. The collision theory of reaction rates. In the last video, you heard me use the term collisions a lot. I hope you realize that there are collisions between the reactants participating in the reaction. But when you talk about that, we want to actually use this term, the collision theory. You want to use collision theory. Use this term on free response questions. Okay. The whole idea behind the collision theory of reaction rates, and again, this is a theory, and in science, in these physical sciences, a theory is an attempt to explain the why. Why do we see what we see? Whereas a law is simply describing what's happening. So the collision theory, that word theory, is an attempt to explain the why. And what we use that to do is, okay, if this is the why, if we change, this and this and this about the reaction, we should see this result. And the way you test a theory is to try to predict things happening. And so if we use this theory, we can actually predict changes in reaction rates pretty accurately. So the first thing is particles must collide. That's kind of a no-brainer because it's in the name of the theory. Here's the idea. Two particles need to collide here, right? In order to collide, you need at least two particles. Now, you can have more than two, but it is rare. Okay, it's much more rare. And so you can have reactions that have 3 or 4 reactants. That rate, however, is going to be pretty low. It's going to be pretty low. So, like we referred to in the first video, proper orientation of colliding molecules is required so that atoms that come into contact with each other can become products. We have to be properly aligned, right? That proper geometry. They have to be facing the right way when they come into contact during that collision. So not only must they collide, they have to collide facing the correct way. The collision must occur with enough energy, right? This was the sufficient energy. This is the second of those major factors that we talked about having a successful, right? A successful collision. So proper orientation and enough energy. Last video I called this the oomph. You need to have enough oomph to hit each other to overcome the electron-electron repulsion in the valence shell electrons of the reacting species, and must have enough energy to transform translational energy into vibrational energy in order to penetrate into each other so that the electrons can rearrange to form new bonds. What does all that gobbledygook mean? First off, translational energy. Right, we have a particle. Translational energy will bring that particle from over here to over there. That's translational energy, the energy of that particular movement. It's changing locations, right? It's moving. Vibrational energy, the reason we want to take this translational energy and turn it into vibrational energy is because electrons involved in bonds can be vibrated out of position. And if they're out of position, that's going to make those bonds easier to break. Remember, a chemical bond is a mutual attraction between the nucleus of one atom and the valence electrons of another. And so the species that's that intermediate species between the two bonded atoms is the electron. And so the reason that those two atoms are at that particular bond distance is because that's the bond distance at which potential energy is at its minimum. Remember, nature favors low energy configurations. If we are vibrating or moving those electrons out of that low potential energy configuration, we are raising the total energy of that system. It's actually going to be easier to break that bond. Why? Here's that same energy diagram. Woo. If this is the normal energy configuration of the products, but we start to vibrate it, okay, now those reactants are coming in with this much energy. Look how much closer we are to that activation energy point up at the top of that bump there. So if we can turn that translational energy, right, enough energy of movement into vibrational energy, we can kind of move those electrons out of position. It'll make them easier to break. It's easier to reach that hump in the energy graph. So when we reach this point in the graph, we have a new set of species. We call it the activated complex or transition state. Okay, I'm probably going to say transition state a little bit more because when I was going through school, that's what we called it, so it's a little bit more familiar to me. However, the term activated complex not only does it mean the same thing, I think it sounds cooler, so I'm actually trying to get myself to say activated complex more. But once we reach the peak of this activation energy bump, the activated complex can either fall to reactants, right, fall back, or can move forward to the product. So let's take a look at this graph here. I'm going to zoom in a little bit. Might be a little janky. There we go. All right, so we have two BRNOs. This is the reactant. And so we're going to follow this energy curve all the way up the curve. Once we meet that activation energy, you guys can't probably see this a little bit too blurry, but this is an E sub A. So I'll just write it like this, E sub A for activation energy. Once we've met this activation energy, this is called the transition state or activated complex. And the reason that it's activated is because the bonds that are binding the bromine and the nitrogens in this case are vibrated out of position. And at this point, the attraction between the bromine and the nitrogen and the bromine and the other bromine are about the same. It's about the same. You're not really bonded to either, but you're a little bit bonded to both. That's why it's called a transition state. It's very fleeting. It's very fleeting. It's none of these species actually exist for any amount of time, but they kind of go through this state. That's why it's called a transition state. You transition through this state. And so you move these electrons out of position enough that the bonds will break, and now new bonds will form from here to there. Now, once we're here, once we've added this sufficient amount of energy, you have two options. Once you get to this, you can have the reaction can fall forward, right, down this big loop right here, and you can form some NO and some Br2, right? That would be the reaction going to completion. But once you reach this activation energy here, the reaction can actually fall backwards as well. It can fall backwards just as easily. The reason that we see in some of these, especially exothermic reactions, that more products end up being formed is because in order to go back and reach that activation energy a second time in the reverse reaction, notice they're actually starting at a lower energy configuration, and to get up to that activation point actually requires more energy than it did to start from this side. So it's actually easier, right, to get from these reactants to these products than it is to get from these products back to these reactants. Now, it's totally possible, right? Forward reaction and then reverse reaction. But this one's going to be a little bit more likely because it's more thermodynamically favorable, aka exothermic. fix my camera back out here so I can see my whole page. Is that good enough? A little bit further. All right. So let's move on to chemical reaction rates. So let's actually look at some reactions. So the speed of a reaction is expressed in terms of the rate, right? It's some measurable quantity. We have to be able to measure it. However much that measurable quantity is changing per unit time. The rate of a chemical reaction is measured by the decrease in concentration of a reactant or the increase in concentration of a product per unit time. Now remember, like we said in the last video, concentration in chemistry is going to be, use that capital M, right? Molarity. Or you can write it moles per liter. Also, don't forget that it can be written, especially because the software that some people use to write questions doesn't allow this to happen very naturally. And so they write moles times liters to the negative first. I hope you remember that anything raised to the negative first is actually going to be inverted and means the same thing as this. So don't be fooled if you see this representation of concentration. It means the same thing. Brackets with that species, the concentration of that species. When writing rate expressions, which is what we're going to do on the next page, they can be written in terms of two things, right? So we're talking about decrease in reactant concentration or increase in product concentration. So reactant disappearance, right? The reactants are disappearing. They're going away. Why? Because they're creating products. And so when we go to actually write down our rate expression, which is the same thing as rate law. Rate expression is the exact same thing as rate law. Same thing, right? Same thing. Anytime we have the change in concentration of the species over time, we're going to add a minus sign out in front because that's a reactant disappearance. Or product appearance, right? Because the products are appearing, they're being made, so they're showing up. And so we're going to represent that with a plus mark. So anytime we look at the rate of product appearance, right, we're going to throw a plus mark in front of this expression because it's showing up. Flip the page. So rate is not constant. It's not constant. Luckily, we won't be doing too much of this difficult stuff, but we do need to know that rate is not constant. Well, it can be, but you guessed it, but it's rare. Rate can be constant, but it's really, really rare. So for our purposes, rate is not constant. It changes with time. When we look at graphing data of an experiment, it'll show, we can show the average rate of reaction, the average, right? Like from here to there, the average. We can look at that slope, but it doesn't represent the rate at any one of these particular points. It's the rate overall. It's the average rate. One of the things that we will do is we will find the instantaneous rate, right? Which means the rate at any particular instant. The rate at any particular instant is the instantaneous rate, the rate at that instant. We can find that by computing the slope of a straight line that is tangent to the curve at that time. Right? A straight line that is tangent to the curve at that time, aka at that instant. So let's zoom in on this graph one more time, or for the first time, but we're going to zoom in again. So when I look at this graph, there's a couple of things that I can read really, really easily, and hopefully you can too. So let's look at this. This is the NO2, and let's see. Oh, and by the way, we're using this reaction here. By the way, this is a reaction that we're using. So I'll write this again up here. Is that gonna be best for you guys to see it? 2 NO2s reaction to form O2 plus 2 NOs. Now we know what this equation is, but we don't have to. We can actually figure it out from this graph. I know that NO2 is a reactant. Say NO2 right here, I can tell it's a reactant. How can I tell this is a reactant? Because at 0, by the way, this would be 0, right? The origin. At time 0, there is some of it. There is some of it. Therefore, it's a reactant. You have to start with this stuff. I know that NO and this O2 are going to be products, not just because I already know what the equation is, but because at 0, the concentration, right, is over here, the molarity right there, concentrations are 0. Okay, there's none of them, but they increase. Boom. As time goes on, there's more of it. So what's disappearing? Follow this chart. See how the concentration goes down over time. That's a reactant because it's going away. It's reactant disappearance. So I'm going to give this that negative sign in front of the rate expression. Products, notice that it is appearing. It is appearing as the reaction goes. So this is going to have, there's more of it. This is product appearance. And so I'm going to give that a positive sign in front of the rate expression. Now, you might wonder, well, what about the coefficients? Okay, how am I supposed to get the coefficients out of this graph? Well, this is going to take a little bit of guesstimation, but it's not that hard a guesstimation if you know what you're looking for. These curves represent concentration at any particular time. We know just by looking at the curve of the O2 and the curve of the NO that there is a larger rate of the NO appearance than there is of the O2 appearance. And in fact, if we were to count, for example, just like, I don't know, at 100 seconds, let's see if I can go straight. Oh, almost get in. You can actually count, and you'll actually see, if you're do your counting, that this point at 100 seconds is about twice the concentration of O2 at 100 seconds. About twice that. It's about twice that. And so we need we're going to get about twice as much NO as we are getting of O2. Once we do that, we can see that the shape of the curve of NO2 more closely resembles the curve of NO as compared to O2, I'm sorry. If NO2 is going to have the same coefficient as O2, we would need to see this curve come out a lot more shallow. And so just by looking at this graph, we can determine that the equation would be 2 NO2s reacting to form 1 O2 and 2 NOs. All right, zoom out again. Bear with me. All right. Now, you can do this by looking at this graph. Like I said, it takes a little bit of eyeballing, even though the eyeballing isn't that tough as long as you know what you're looking at. What you can also do is you can refer to data. A lot of times the AP exam will give you data tables just like this. Now, you don't need to use all of this data. You just need to use specific points. And you're going to see the exact same concept or the exact same relationships at every time. So, I was like, how do I know if I'm supposed to use 100? Johnson used 100 when he was talking about his graph over here. Well, I just randomly picked that because it was a number over here. I could have picked 150. I could have picked 200, 250. I could have picked 300. The same thing I'm about to show you occurs at all of these. Okay. Let's see. My camera's freaking out a little bit. I don't know what that is. Okay. So we have our, let's go to 100 seconds again. So we have NO, here's my concentration, right? Moles per liter, that's molarity. So I have my concentration of NO and my concentration of O2. Now, it's not absolutely perfect because, well, we don't have enough exactness here to show that perfectly. Notice how the concentration of NO is about twice that of O2. And go down here at the 300 seconds, just randomly. Here's a concentration of NO. Here's a concentration of O2. Again, it's about twice. It's about twice that. So there's your relationship between your two products there, the O2 and the NO. What else I want to show you? You can also establish which one is a reactant, which ones are products by looking at the concentration. Notice that at time 0, here we have stuff. We have NO2. And as time goes on, the concentration gets smaller and smaller and smaller. Whereas with both of these, we start with none of it. Okay, we start with 0 of it, and then as time goes on, we get more and more of those two species. That makes them the products. All right, reaction rate. How do we express it? I've been talking about rate expression or rate law. How do we actually write this? It is expressed as the change, right, delta, the change in concentration of a reactant per unit time. And so we would draw that. You can write that, or a little bit more intuitive for me to write delta, concentration of A, over whatever the change in time is. Now, you can either focus on the disappearance of reactants, or you can focus on the appearance of products, either one. But if you are looking at the change in reactants, okay, the rate is always going to be negative. Why? Because the reactants are disappearing. The change in concentration of product is always going to be positive. Why? Because they are being made. They are appearing. So if we consider the exact same equation we just looked at that graph, we see that oxygen can appear only half as rapidly as nitrogen dioxide disappears, while nitrogen monoxide appears twice as fast as the oxygen appears. And we can see that relationship in the data table. Okay, if you want to go back and double check for yourself, you will see that in the data table. So if you examine the data table and you can calculate the average rate at which NO2 changes in the first 50 seconds. Remember the square brackets are shorthand for molarity. We can determine the rate at which NO2 is disappearing, hence the minus sign. We can take, let's see, so we're going between 0 and 50 seconds. Okay, so I'll go up to 0. What's my concentration there? Right, concentration at 0 is 0.01. There's my 0.01. And then 50 seconds, or sorry, 50 seconds, 0.0079. 0.0079. And then my change in time was 50 seconds, right? So that's on the bottom. So I am satisfying this format here. Now, I do have this same minus sign, right? These two minus signs are the same. I want to have a negative number here, so I'm going to subtract the larger concentration so that when I take, all right, so that's the same minus sign I get from reactant disappearance. That's going to cancel out with this minus sign, giving me a positive overall rate. All right, you see how that works? So simple calculation, that minus that divided by that ends up being a pretty small number as it happens. And I'm having 4.2 times 10 to the negative 5 moles per liter times seconds, or molarity times seconds to the minus 1. Remember, I can write that as molarity per second. I can write that as moles per liter times seconds. They're all the same thing. They're all the same thing. Note that rate is not constant, but it decreases with time. It decreases with time. It goes down because realize what's happening as the reaction progresses. The amount of reactant is going down, right? It's disappearing. It's being turned into product. And so, especially if you have a certain situation that has to happen for your reaction to progress, as your reactants disappear, you're going to have less and less of that situation occur. You're not going to have those successful collisions. You're not going to have those successful events. And so you're going to see the rate goes down over time. As we saw in that graph at the top of your page, you see that the reaction rates start pretty steep, right, at 0, but then they start to even out. And so we see that here, right? Reaction rates go down, go down, go down as time increases. Go down, go down, go down. But I say again, to determine the value of the rate at a particular time, which is the instantaneous rate at an instant, compute the slope, right? The slope, y equals mx plus b. Compute the slope of the line that is tangent to the curve at that point, right? So let's go back up to the graph and let's take a look at this real quick. Why is the why do we have the negative on NO2? So check out this line right here. That is the straight line tangent to this point right here. This is a point on the NO2 reaction curve, and I simply calculate the slope, right? Rise over run, rise over run. That is the same thing, right? Slope equals rise over run. But realize on this graph, the rise, right, the y-axis is molarity. So slope, if rise equals molarity, I'm going to substitute molarity in for rise. And run, look what's on the x-axis. Time. And so my rise over run turns out to be concentration over time. See how that makes this easy, right? So if slope equals rise over run, and rise over run equals molarity over time, and molarity over time equals rate, that means slope equals rate. Got me? Got me? Slope equals rate. Cool beans. Cool beans. Oh, forgot a question. Why is the slope of NO2 negative? Don't say because it's going down. That's what negative means. Why is it going down? Because the concentration of NO2 is going down. It's disappearing. All right. So we have our ability to express a rate law. Okay, we have the ability to express a rate law. But we want to introduce relative rates. Okay, means that they relate, right? They relate, relative, relate, relative. Whoa, my hand's in the way. Relative, they relate. How they relate, their relative rates. How do they relate to one another? We can consider the appearance of products. Okay, let's look at that same equation again. We can consider the appearance of products, which again, appearance of products is going to come with a positive sign, or the disappearance of reactants, that's going to come with a negative sign. The reactants concentrations is declining, right? It's going down. That's why the slope of our line that's tangent to the curve of NO2 was negative. It's a negative slope. The concentration is declining. The product is increasing. We need to respect the algebraic sign and respect the stoichiometry. And so we just went over how we're going to respect the algebraic sign, right? It's the slope of that tangential line. But how do we respect the stoichiometry? Stoichiometric coefficients. Remember these? A 2, a 1, a 2. We have to remember to balance our equations. Now, before we get into the reaction rate, I want to remind you, you have to balance this appropriately. Once we've balanced this appropriately, all we're going to do is turn each of these coefficients into a fraction. And what do? We put each of these coefficients, these stoichiometric coefficients, as the denominator in our relative rate. How do we do that? How am I supposed to do that? How am I supposed to do that? Well, all we're going to do is put a 1 over everything. You see that's a 1. I just put a 1 over that. Put a 1 over that. And so I've made the stoichiometric coefficients of each of these species a fraction. Okay, I've made it the denominator, the coefficients a denominator. Now, if I'm going to make a relative rate, right? So my relative rates, I have my change in NO2 over change in time. I have my minus sign right here because I'm respecting the algebraic sign. NO2 is a reactant, so it's going to have that minus sign, equals NO, concentration of NO over change in time, is equal to change in O2, concentration, over change in time. Now, the way we try to take into consideration that O2 is going to appear at half the rate that NO is, and also that same relationship with NO2, is we are going to take these fractions and we're just going to stick them in front of the relative rates. Excuse me. So I'm going to take this fraction and I'm going to stick that right there. That's the 1/2 right there, 1 over 2. That's where I got that. Here's the NO. Sorry, it's a little bit out of order, but here's the NO. Here's the half. There it is. There it is. Now, this is 1 in here. It's understood that there's a 1 there, so there's my 1 over 1 right there. And it's foolproof. All right, you balance your chemical equation, right? So you have the correct stoichiometric coefficients, and then you turn that stoichiometric coefficient into the denominator of a fraction, and boom, there is your relative rates. Now, relative rates, meaning you're going to relate one rate to the other. Relative rate, comparing to one another, as opposed to absolute, right? We're not doing that. We're going to need a constant to do that. Right now, we're just doing relative rates. Now, up here, I have 3 of them written. You're never going to relate 3 rates to one another. You're just going to be relating 2. I have 3 written up here just for completeness. Now, if you don't like fractions, you can always go through this and multiply them all by 2, and that would turn them into not fractions. Okay, they'd be perfectly correct, but that's just one more step that you could potentially screw up. So for this situation, I could turn them all into whole numbers by multiplying them all by 2. So if I multiply them all by 2, this would be this coefficient right here. That would be what would that be? A -1. This would be sorry, that'd be a +1, and then this one would be a +2, right? So that would be your coefficient right there for your relative rates. Again, You don't have to do that. That's just if you can't stand fractions. So, again, let's do the same thing, or let's show how we do the same thing with a different equation. So, balanced chemical equation, I'm going to just stick a -1. Okay, there's a 1 here, so that's understood. -1, -1. And I have the negative sign because this is a reactant. It's disappearing. Okay, negative slope. Think back to your graph. It's my change in pH3 concentration over that time. I take my 1/4. That's my coefficient there. My P4 concentration over time is a 1/1. You guys can see the 1 is assumed right there, but it's positive because it's a product. Then I have my H2, my hydrogen, my change in concentration there. And then, actually, I forgot. And then my timer over here, and then 1/6. Where did I get that? From this 1/6. Boom. Now, if I'd have been on my game, I would have whited this out. Okay, but we're going to take a look at this exercise anyway. And yes, this is the answer. This is the answer. What are the relative rates of change in concentration of the products and reactant in the decomposition of nitrosyl chloride, which is NOCl? So, we're decomposing this reactant. Okay, so this is a reactant. So, my change in concentration of my reactant over time is going to be a negative. Why? Because it is a reactant. Here's my NO, my Cl2. They're both are changing concentrations over time. Both of these are products, so they're both going to get positive numbers. Now, for my coefficients, I'm going to throw -1 over all of them. So that means I'm going to put a 1/2 in front of my rate for NOCl. I'm going to throw 1/2 in front of my rate for NO, and I'm just going to throw 1 in front of my rate for Cl2. Again, relative rates. This relative to that, or that relative to that, or that relative to that. All right, so you're not going to have to do all three. You're never going to have to use all three, but you will have to use 2 of them pretty regularly. Again, this is a relative rate, not an absolute rate. All right, guys, go ahead and move on to the next video.